In this unit, we're going to have a look at 2 points and the line joining the 2 points. We call this a straight line segment. And I'm going to show you how we can calculate the distance between the 2 points, or in other words, the length of this line segment, and how we can calculate the coordinates of the midpoint of the line segment. Now, before we do that, I'd like to revise some facts about the coordinates of a point. Suppose we choose a point, let's call this point O, and suppose we draw a horizontal line through that point, and a perpendicular line, a line at 90 degrees, also through that point. We call these two perpendicular lines axes. And this horizontal line, we'll call it the x-axis and label it with the letter X. And the vertical line, we'll call this the y-axis and label it with the letter Y. Now, on these axes, we draw a scale. And what we do is we draw what's called a uniform scale. That means it's evenly spread along the axis, and so on. And on the y-axis, we do likewise. We put a uniform scale on the y-axis. And the point of doing that is that we can then measure distances in the x direction and in the y direction. Now, suppose we choose any point at all in the plane. Let's choose a point here, and let's call this point A. What we can do is we can measure the distance of A from the vertical axis. So we can measure that distance in there. And because that's a distance in the x direction, we call it the x-coordinate of the point A. We can also measure the distance from the horizontal axis. And because that's measured in the y direction, we call that the y-coordinate of A. And these two numbers, the x-coordinate and the y-coordinate, we write in brackets after the letter A itself. And we call x, y the coordinates of the point A. We also refer to x, y in the brackets like this as an ordered pair of numbers. It's clearly a pair of numbers, and it's an ordered pair because the order is very important. We put the x-coordinate first, that's the distance from the y-axis, and the y-coordinate second, that's the distance from the x-axis. So now we have a way of specifying precisely where in the plane our point of interest lies. If we move to the left-hand side of the y-axis, then what we have are negative x-coordinates, because as we move to the left, we count down from 0, so -1, -2, -3, and so on. So anything to the left of the y-axis will have a negative x-coordinate. And similarly, if we want to come down below the horizontal axis, if we want to come down here, we count down from 0, -1, -2, -3, and so on. So any point with a negative y-coordinate will be below the horizontal axis. Let's plot some points and see where they lie. Now, I've prepared some graph paper for us. So here's my piece of graph paper. You can see my x and my y axes and my uniform scales drawn on the two axes. And let's plot some points. Here's the first point, point A. And let's suppose point A has coordinates 3, 2. Let's see where that is. Well, A has an x-coordinate of 3, so we move in the x direction a distance 3, and a y-coordinate of 2, so we're moving up from the x-axis a distance 2. And that takes us to this point here. X-coordinate of 3, y-coordinate of 2. Let's have another point. Let's have point B. Let's switch those round. 2, 3. Let's see where that is. Now, with an x-coordinate of 2, so we've got to move a distance 2 from the y-axis. And a y-coordinate of 3 means we move vertically. So 2 across, 3 up, takes us to this point there. And that's my point B. Let's have some more. What about this point, C, which has an x-coordinate of 0 and a y-coordinate of 3? Let's see where that is. Well, an x-coordinate of 0 means we move no distance at all in the x direction. So we stay on the y-axis. And we want to be a distance 3 upwards from the origin. So there's my point C. Point D, let's suppose that's minus 3, 0. So I've introduced a negative x-coordinate now. Remember, with a negative x-coordinate, we're moving to the left-hand side of the y-axis. We want to move a distance 3. 1, 2, 3. So we're on this line here. And a y-coordinate of 0 means we don't move up or down at all. So we're at that point there. So there's my point D. Let's have a couple more. E, minus 2, minus 3. So we've got both a negative x and a negative y value. Minus 2 on the x means we move to the left, distance 2. Minus 3 on the y means we move down a distance 3. So we're down there to get to point E. Final one, 2 minus 2. Let's see where that is. X-coordinate of 2 means we move to the right a distance 2. Y-coordinate of minus 2 means we move down a distance 2. So there's point F. OK, so now, given any ordered pair of numbers representing a point in the plane, you know how to plot where it is. We know how to locate it. So now we know how to plot the points. Let's see if we can plot 2 points and find the distance between the 2 points. Okay, so some more graph paper here. And let's suppose we pick any 2 points, and let me suppose the first point, let's call it A, has coordinates 1, 3. Let's put that on the graph. X-coordinate of 1, y-coordinate of 3 means we are 1 across and 3 up, so we're at that point there, that's A. And let's choose my second point to be 4, 5. X-coordinate of 4, y-coordinate of 5 puts me there. So 2 points. Let's join them. And that gives me my straight line segment. And what I'm going to do is I'm going to show you how we can calculate the length of this line segment, or in other words, the distance between points A and B. Now, the way we do this is as follows. We look at the point A, and we'll draw in a horizontal line through A. So because this line is horizontal, it's parallel to this x-axis. I'm going to draw in a vertical line through B. And again, because that's a vertical line, it's parallel to the y-axis. And so this angle in here must be 90 degrees. And we see what we've done is we've formed a right-angled triangle. Anywhere along this horizontal line has a y-coordinate of 3. So in particular, the y-coordinate at this point here, where the right angle is, must be 3. Let's call this point C. Its y-coordinate must be 3. Now, anywhere on this line has an x-coordinate of 4, the same as the point B. So the x-coordinate here must be 4. So now we know the coordinates of this point as well. Let's put the coordinates of B in, 4, 5, and A in, 1, 3. Now what I'm going to do is I'm going to show you how we can calculate this distance in here and this distance in here, because then we will know the lengths of 2 of the sides of this right-angled triangle. And then we're going to use Pythagoras' theorem to get this length, because this length is the hypotenuse of this right-angled triangle. Let's look at this distance here. Now the total distance from the x-axis up to point B is 5, the y-coordinate of B. So the distance all the way up there is 5. The distance from the x-axis up to point C is 3. the y-coordinate of c. So that distance is 3. So this distance that we're really interested in here must be the larger distance subtract the smaller distance. 5 subtract 3, which is 2. It's important that you recognise that we've calculated this distance by finding the difference of the y-coordinates. 5 subtract 3. What about this distance in here? Well, the total distance from the y-axis to this dotted line is 4, which is the x-coordinate of b, or the x-coordinate of c. This shorter distance from the y-axis to point A is just 1. That's the x-coordinate of A. So that's 1. So the distance we're really interested in is the larger minus the smaller, 4 minus 1. And 4 minus 1 is 3. And again, 4 minus 1 is the difference of the two x-coordinates, 4 minus 1 giving you the 3. So now we know the length of the base of this triangle is 3, we know its height is 2, and we can use Pythagoras' theorem to find AB. Pythagoras' theorem will say that AB squared is the sum of the squares of the other two sides. AB squared will be 3 squared plus 2 squared. 3 squared is 9, 2 squared is 4, and 9 and 4 is 13. So AB squared is 13, so AB, which is the distance we want, is going to be just the square root of 13. Okay, so knowing the coordinates of the 2 points, we can find the lengths of the sides of this triangle and then use Pythagoras' theorem to get the hypotenuse, which is the distance between the 2 points. Now that's all well and good for the specific case we looked at, but what I want to do now is do it more generally. Instead of having specific points, I want to take 2 arbitrary points in the plane and see how we can find the distance between the 2 of them. So again, let me have a y-axis and an x-axis and an origin. And let's pick our first point, let's call it A, and let's suppose it's got an arbitrary x and arbitrary y coordinate, so let's call those x1 and y1. So there's my point A. I'm going to take a second point, let's call that B, and let's suppose its x-coordinate is x2, y-coordinate is y2. So these are arbitrary points now, could be anywhere. We're going to try to find the distance between the 2 points, or in other words, the length of this line segment. As before, let's put in a horizontal line through A and a vertical line through B. To form this right-angled triangle here. Let's call this point C. What are the coordinates of point C? Well, anywhere along this horizontal line will have a y-coordinate which is y1, because that's the same as the y-coordinate of A. So the y-coordinate of C must be y1. What's its x-coordinate? Well, its x-coordinate must be the same as the x-coordinate of B, which is x2. So x2, y1 are the coordinates of point C. Let's calculate this distance in here. Now this distance is the difference in the y-coordinates. The y-coordinate of B subtract the y-coordinate of C. So this is just y2 minus y1, the difference in the y-coordinates. Similarly here, this distance is the x-coordinate of C, which is x2, subtract the x-coordinate of A, which is x1. So this distance is simply x2 minus x1. And now you'll see we know the base and we know the height of this right-angled triangle, and we can use Pythagoras' theorem to get the hypotenuse, which is the distance we require. So Pythagoras' theorem will say that AB squared, the square of the hypotenuse, is the sum of the squares of the other 2 sides. That's x2 minus x1 all squared, plus y2 minus y1 all squared. And then if we want AB, all we have to do is square root both sides. So AB will be the square root of x2 minus x1 all squared, plus y2 minus y1 all squared. And that is the general formula that we can always use to calculate the distance between two arbitrary points in the plane. Let's look at a specific example. Suppose we want to find the distance between the points, say, A, which has coordinates -1 and 3, and B, which has coordinates 2 and -4, for example. How can we use this formula to find the distance between these 2 points without actually drawing all the points? Well, using the formula, AB will be the square root. We want the difference between the x coordinates. So that's 2 minus -1, all squared, plus the difference between the y coordinates, which is -4 minus 3, all squared. So that's the square root of 2 subtract -1 is 3, and 3 squared is 9. -4 minus 3 is -7, and -7 squared is plus 49. So finally, AB will be the square root of 9 plus 49, which is 58. That's the distance between those 2 points. We're now going to look at how you can calculate the coordinates of the midpoint of a straight line segment. Before we do that, let me just consider this problem. Suppose we have an x-axis and we have some points on the x-axis. So suppose we have 1, 2, 3, 4, 5, and so on. Let's choose 2 points on this x-axis. Let's suppose we pick this point where x is 2. Let's call that A. And this point where x is 4, let's call that B. And ask yourself, what is the x value at the midpoint of the line segment AB? So we're looking at this segment AB, and we want to know what the x value is at the midpoint. Well, I think it's fairly obvious from looking at it that the x value at the midpoint is 3. Another way of thinking of that is that 3 is the average of 2 and 4. Because if we average 2 and 4, add them together, divide by 2, 2 and 4 is 6 over 2, which is 3. So in other words, the x coordinate at the midpoint of a line segment is the average of the x coordinates at the 2 ends. Just to convince you of that, let's have a look at another problem. So we have 1, 2, 3, 4, 5, 6, and 7. And let's suppose this time we pick, say, the point 3 for A and the point 7 for B. And we're looking at this straight line segment here between A and B. Again, it's rather obvious from looking at it that the x value at the midpoint is 5. And if we average the x values at the beginning and the end of the line segment, 3 added to 7 divided by 2, that's the average of the x values, is 10 over 2, which is 5. So in a more general case, in a few minutes' time, we'll see that when we want to find the coordinates of the midpoint of a line, we just need to average the values at either end. Okay, let's look at a more general one. Suppose we have 2 points. Suppose A is the point 2, 3, and B is the point 4, 5. Let's plot those, and then we're going to try to find the coordinates of the midpoint of the line joining them. So A is the point 2, 3. So here's point A. And point B is 4, 5. So B will be up here, round about there. And there's my line segment AB. We're interested in the point which is the midpoint of this line. So let's pop that on there. And let's call it point P. And because it's the midpoint of the line, we know that this length must be the same as this length. AP is the same length as PB. Let's put some other lines in here. A horizontal line through A, a vertical line through B, horizontal line through P, and a vertical line through P. And let's label some of these points that we've created C and D and E. Now let's look at the line segment from A to E. Okay? Sorry, Peter. Lost it.
What you'll do on cue is you'll dampen it, look up at the camera and speak, okay?
Yep. Now let's look at the triangle ACP and the triangle BD. Sorry, the triangle. Yeah. Now let's look at the triangle ACP and the triangle PDB. Both of these triangles are right-angled triangles because they both have a right angle here. Both of the triangles have the same hypotenuse which has the same length because they both have the same length there and there. Also, this angle in here is the same as this angle in here because they're corresponding angles. So in fact, because we've got two angles and a side in the first triangle corresponding to two angles and the side in the second triangle, these two triangles are what we call congruent. Congruent triangles are identical in every respect. And in particular, what this means is that this length from B down to D must correspond and be the same as this length from P down to C. So in other words, because these two lengths are the same, BD and PC, which is the same as DE, then this point D must be the midpoint of the line from E to B. So the y-coordinate of D must be the average of the y-coordinates at E and B. Now the average of the y-coordinates at E and B is 3 plus 5 divided by 2, which is 8 over 2, which is 4. So the y-coordinate at D must be 4. What about the x-coordinate? If we look at this line from A to C, because the triangles are congruent, then this distance from A to C must be the same as the distance from P to D, which is the same as the distance from C to E. So in other words, because these two distances are the same, C must be the midpoint of AE. And because C is the midpoint of AE, its x-coordinate must be the average of the x-coordinates at A and E. Now the average of those x-coordinates is 2 plus 4, which is 6, divided by 2, which is 3. So the x-coordinate here must be 3. So the x-coordinate is 3. We know the y-coordinate is 3. At this point, we decided that the y-coordinate was 4, and we know the x-coordinate is also 4. So now we can read off what the coordinates of point P are. P will have an x-coordinate of 3 and a y-coordinate of 4. Now that's very complicated. It seems very complicated, but in practice it's very simple. Let's just look at these numbers again. The x-coordinate at the midpoint, which is 3, is just the average of the two x-coordinates. 2 plus 4 is 6, divided by 2 is 3. The y-coordinate at the midpoint, 4, is just the average of the two y-coordinates, 5 and 3, which is 8, divided by 2 is 4. So in general, if we have a situation where we've got a point A, x1, y1, and point B, x2, y2, the coordinates of the midpoint of the line AB are the average of the x-coordinates and the average of the y-coordinates. Let's just look at a simple example just to hammer that home. Suppose we have a point A with coordinates 2, minus 4, and B with coordinates minus 4 and 3. So 2 points, and we're interested in the coordinates of the midpoint of the line AB. So let this point be P. The x-coordinate will be the average of the two x-coordinates, which is 2 added to minus 4 over 2. And the y-coordinate will be the average of the two y-coordinates, which is minus 4 added to 3 divided by 2. And if we tidy that up, we'll get 2 subtract 4, which is minus 2, over 2, which is minus 1. And minus 4 plus 3 is minus 1. Minus 1 over 2 is minus a half. So there is the coordinates of the midpoint of the line joining A and B.